References and borrowing are a result of the way that Rust deals with ownership of memory. Since there are specific rules around duplicating and disposing of this memory and specific values that are stored in different spots of the memory, it's important to understand how these values are duplicated and disposed of in the memory. Because of the way Rust deals with ownership, it's important to understand the rules of referencing and how to dispose and access the values stored at specific memory addresses. So looking at this piece of code right here, we can see that we have some string that we define. And then down here, we have what's called a reference. Now, we haven't seen this before, but just to make sure we understand what this, but just to make sure it's understood what is meant by a reference, I like to imagine sort of a block of memory. Then you can have different slots in the memory like this. Let's say we have some data at this address in the memory. The memory is represented by some hexadecimal number. So it'll be 0x and then a bunch of letters or numbers that represent sort of where the value is being stored in the memory. So what we can do is, as soon as we store a value there, accessing it is a little bit trickier than just calling the last variable s1. What we need to do is have this little and character, which is basically saying we have this pointer s1, which points to some string stored in our memory. And now what we're going to do is call the value of that address by using the and character. So we can do that. We can pass in the value of the pointer and calculate the length by passing in the value of the address at s1 into the calculate length function. Now, this is a little bit counterintuitive to what we were going over before. We have this function and we are returning something from the function. So you'd think that the value or like the memory address would sort of pop as soon as we go out of the scope of the function, because that's sort of how Rust deals with ownership. But it's a little bit different here because the actual reference of the string with this symbol right here does not actually own the pointer value. So it doesn't directly change it. It's just sort of referring to the value of that string at this memory address. So we can safely go into this function and return the value string dot length of whatever we're passing into it and safely pop it out without losing some scope or some access to another variable. Now that we have access to the reference of some memory address, let's say S1, we can do a lot cooler things with the value. So another thing we can do deals with slices. So if we have a string hello, we will be able to access each individual character with one sort of index operation instead of just having some pointer to H and then having to step character by character until we get to the end. So we can do that through something like this. So we have this syntax, let hello equal to a reference s. So this grabs the value hello world up here. And then this sort of hard bracket indexing style is very similar to other coding language. So it's very similar to other coding languages. And it's also very similar to what we saw previously with for loops. So if we had some for I in 0.5, this would be like a range from 0 to 5, and it would print, or not print. So it would do any operation we ask it to do inside the for loop. So it's very similar. We're saying this is indexing from 0 to 5. So it'll go and count 0, 1, 2, 3, 4, and then be exclusive on 5 and return hello. So similar to hello, we have world. Intuitively, we'd just be going and accessing world, which is exactly what it does with indexes 6 through 11. So it's sort of a cool thing. As soon as we get the value, we can do other interesting things such as index character by character of the string. So one problem that we run into once we actually have access to the value is changing it. So if we wanted to change it, we couldn't just say let s equal to the string, grab a reference, and then say like, oh, at s, the reference value of s from 0 to 5 is now equal to something else instead of hello. This wouldn't work. But what we can do is use a mutable reference. So looking at this piece of code right here, we already see some differences from what we saw previously. So instead of just let s equal to some string, we are adding in this mute keyword, which allows us to change the value of the string hello using mutable references. So after we do that, we can define a variable r1, which will be a mutable version of the reference of s. So instead of just saying the and character and then s, which would point to the reference of hello, well, not necessarily point to, but it would directly equal to the string hello, we can now make it mutable. And what this does is it looks at the pointer s and what value is stored there, and it allows us to change it. So what we can do now is, now that we have R1, we could say like R1 is equal to some other string, R1 dot push. Like this, we could have R1 dot push string. This is not exact syntax, but we could add on some other string like space and then world, and this would be completely fine. So since Rust is very strict with the way that memory is stored and accessing values and changing them as well, we do have rules with referencing these variables. So if we create a reference that's mutable, that means the compiler is saying at any point in the program, in the scope of this reference, you can change the pointer s and the value stored at it, in this case hello, to anything you want to. You can basically edit it. As soon as we create within the same scope another variable R2, which is a mutable reference to s, this causes problems. So the compiler is saying that we have two different references to s that we could change at any time. And for example, if we were to change them at the same time, there could be conflicting errors in the compiler. So we're not allowed to do this. So if we were to say println the two values, add R1 and R2, we would run into an error because we're not allowed to access two different mutable references at the same time. And one more rule that's behind mutable and immutable references of strings is that we're not allowed to have mutable references and immutable references in the same scope at the same time. Now, this is because, for example, let's say you had a user accessing an immutable value of the string hello in some scope. They don't expect this to just completely change in the same scope while they're using this immutable reference. And if we were allowed to have some mutable reference to s and also an immutable reference to s in the same scope, then the user of the immutable reference, with the expectation within that scope that the value is not changing, could suddenly have a surprise change to that value because there is access to a mutable reference as well. So this results in a big problem. As soon as we define a mutable reference to s in the same scope as a non-mutable reference, we run into a problem. So the general rule for mutable and immutable references is you can either have an infinite number of immutable references because there won't be any change to them. You can just access them as many times as you want, or you can have one mutable reference. And that reason being, you can't have multiple mutable reference such that you're changing the string or the reference to the string in different ways at the same time. That would not make sense to the compiler. With this, you understand accessing values of different points in memory and also changing it with mutable references to that value. In the next video, the topic will be about dangling references, which is similar to rules of borrowing and references, except it'll be dealing with when we have a slot of memory where there might not necessarily be a value pertaining to that slot, which will give us an error. Definitely make sure to understand these rules before moving on, but once you do, I will see you there.